So good morning. So we're going to find this impedance of this circuit, find Z, the impedance, using complex numbers. Yeah. And the beauty of it is you can solve it using other software. So I'm going to talk a little, I've used Wolfram Alpha, which I've mentioned to you before. I've used Wolfram Alpha to find the answers, basically. It's cheating in a way. It's not cheating, it's using your common sense.
Verifying.
Yeah. So when you do this in the assignment, it's obviously worth your while. Work out your basic values, but use something like Wolfram Alpha to work out the actual answer, and you know you've got it right. So when you've got written out your equation, you can just jump to the final answer, can't you? Rather than trying to do them. Okay, let's have a look then. So I've got a circuit, and you've got a resistor, three parts of a parallel. So we've got a capacitor, and then we've got an inductor. Now, an inductor's always got resistance because it is a coil of wire generally. So it's always got a resistance of some degree. In fact, if you look at a data sheet for an inductor, it will actually give you what they call the DCR value, the resistance of it. And then we've got another resistor in parallel as well. So let's see what we get as the impedance. This is where you'll see how complex numbers comes in useful, because not only does you'll get a real part, which is going to be the resistance, and you get an imaginary part, which is the reactance of the capacitor and inductor combined. So let's see how it works out. Firstly though, let's find out what the impedance is of the capacitor and the inductor. So it's XC, so that's 1 over 2 pi the frequency, which is 60, times the value of the capacitor, which is 15 microfarad. So 15 times 10, so millimicro, so minus 6.
Yeah, 10 to the 6.
So if I just number crunch that, I get, and I've got the answers here. Right, what I've done here, and I don't know if you'll follow this, because quite often it does confuse people. I've only done the bottom part of the equation, so I've not done the inverted part. Not dividing 1 by 8, and I've got this answer, and I've done that for the reason, the crafty reason. Oh, what I forgot to do is when we're doing complex numbers, we have a J there in front, or an I if you do using conventional complex numbers, but we use J of course. So J, and the answer to this was J 5.655 times 10 to minus 3. So I've left my answer like that in that form, which is totally correct, as is that really. I've left it in that form. There's a reason I've done that, to save myself a bit of work later on, and hopefully you'll follow that when I get to it. So XL is simply J 2 pi, L is 80 millihenries, so I'm going to write this like this, 0.08, so that's 80 millihenries, times, forgot the frequency, times 60 for the frequency. Okay, I could have just put 120 pi in, couldn't I, because 2 times 60 is 120. And the answer to that is J30.16. The units of these is ohms, of course. Okay, or use the letter R if you wish. So 30.16. So the circuit is like this. I'll explain it. We're adding in parallel, so we've got to do the inverted adding method. By that I mean this. So the impedance is 1 over Z. So I'd have to invert my final answer when we get there. So it's going to be 1 over R1 plus 1 over XC, which is that there. That one, plus, and then these are in 1 over for these, but these are in parallel, so it's going to be 1 over, so where are we, R2, so it's R1, R2 plus XL. Okay, so that's the formula. So once I've solved it, and we're going to solve it using complex numbers, then I have to invert my answer. It's a little bit long-winded by hand, but it's quite quick if if you use software to do your calculations. So that means, so what I'm saying I've got is this, 1 over z equals, so this is purely a number, 1 over 90 plus, now what I've got here, because my xc is 1 over, this is showing now why I kept it inverted, 1 over j 5.655 times 10 to the minus 3. So what that means is, because it's double inverted, I can now switch that to the top. So what I'm saying is, if I completed the answer, got 1 and divided by that, I would have got a number, obviously. And then I would have ended up going backwards again and doing it again. So I would have ended up with that on the top anyway. So what I've done is just saved myself a step. I know it's not a big deal with calculators, but so that's going to flip to the top. So that's actually done then. 1 over 90, I have to do the maths. This I don't have to do the maths because it's already done for me. And then I've got my final bit, which is 1 over, so R2 is 5 plus J, and XL is 30.16 ohms. Okay, so if you look at it, what I've actually got here is a real number, an imaginary number, a real number, an imaginary number. Now these are easy to solve. This is already solved. This is easy to solve. We can do it by 90. Calculate a job. If you get a nice number like 10 or 100, it's even easier. This one, what do you think I'm going to do to get this? I've got 1 divided by 5 plus j 30.16. So it's a complex number. So how do you think I'd solve this one? So basically we're doing a division with a complex number. And what did we do to solve those?
Is it the rectangle form?
It's rectangle form, yes. So how did we solve rectangle form when we had to divide? What was that method? So while you're thinking about it, let me just put some numbers in. So this is, so 1 divided by 90 is 0.011, recurring actually, that'll do. Plus, and I flip this to the top, that's J 5.655 times 10 to the minus 3, plus what did we do? We had to use the conjugate, didn't we? To solve, when we divided anything by a complex number, we had to use the conjugate. I know the example we did had a complex number on the top and the bottom, it's the same thing. This hasn't got a complex number on the top, though it will have shortly. But yeah, it's got one on the bottom. So we have to get rid of, we can't divide by complex numbers, so we multiply it by the conjugate as a workaround to get rid of it, make it real. So what I'm going to do is I'm going to do it in blue. I'll do it over here. So this I'm going to solve like this. It's going to be 1 divided by 5 plus j 30.16 times its conjugate. And the answer to that will equal our solution.
Right. Is the conjugate where you just swap the symbol?
Exactly, yes. So we're going to have, on the bottom we're going to have 5 minus j 30.16. On the top, we have to have the identical to keep the formula balanced. So we're going to have the same, but that's easy.
Could you not just write that down as 1?
It's 1 times that.
Oh, right. Oh, yeah,
so that's going to be easy to solve because it's just 1 times that, so that's going to stay the same.
Yeah.
But the bottom part, the divider, is going to be the answer to the complex number. Now remember, we had a shortcut for doing conjugates. Remember that? Square that, and add them together. Okay. So that gives me, it's always nice to have the results. If I square that, that's obviously 25. Square that, 30 squared, so that's going to be 900 and something. Don't know off the top of my head, though I've got it written down here. That will give me, I will then end up with, so on the top I will have 5 minus J30.16, because that's just 1 times that. And on the bottom I'm going to have that squared plus that squared. And if you want to check it, if you don't believe me, it's 934.63. Okay? So that's not a complex number, I need to split that up as a common denominator. So I will get 5 over 9, 3, oops, that's a bit messy. 934.63 minus J30.16 divided by the same number, 934.63. Okay with that?
Mm-hmm.
So that bit there is that bit there. This bit solved. So I'm going to rub my blue bit out, so make sure you've got that down. And then I'm going to shove that into there, back into black.
Up to the bottom.
That's our answer there, that
Yeah.
bit.
So that's now going to go into the...
That's going to go into there.
Right.
So we're getting close actually. So it doesn't take long to do this, once you get going.
Oh, that's really simple.
There's a little twist in the tail. We have to do this conjugate process twice. The answer's going to be inverted. So I've now got plus 5 divided by 934.63 minus J30.16 over 934.63. I can now rub that off. So I've now got, getting close. So what I've now got is another calculator job. This is real, this is real, this is imaginary, this is imaginary. So it's not your normal process. Add your real parts together, add your complex parts together. So that will give me 1 over Z to equal, well, we're not going to do it because I have the answer. 1 over Z gives me this. So 0.01646 minus J 0.0266. So that's 1 over Z, but we want Z. So do you understand what I've done there? I've taken the real part and added it together with that. You can calculate it, obviously.
So what have you done to get the 934.16? Because you said...
I've added that bit. So this bit here is being added to this bit. And that's given me that.
Right.
So put that in your calculator, number crunch sheet, and you get that as an answer.
Yeah.
And then I've added together these two. These are the complex ones. Obviously you've got a negative, so it's going to, and that's bigger value than that. That's obviously a small value times 10 to the minus 3. It's going to be a negative answer. So that's 1 over Z, but we don't want 1 over Z. We want Z. That's what we're looking for. Find Z, not 1 over Z. So this is the bad news. You've got to do it all again. You've got to do the
I've got a slightly different. I've got 0.01634 now. Because you've not used a rounded up number.
Probably, because when I'm working these out, the other thing as well is I actually checked this answer on Wolfram Alpha. So what I did was I put into Wolfram Alpha this bit really, but with this at the top, and then press go, hit return, and it gave me this answer.
Okay.
And the beauty of Wolfram Alpha, it's then easy to invert it as well, because I just invert the and put it as an inverse, and it does that for you as well. Obviously, Wolfram Alpha that uses letter I, not J.
Yeah.
So it's all quite So the maths is quite easy. So I know you're going through it, but you don't need to really actually do the maths in your calculator. You just need to put your numbers in. You've got to show your steps on this bit. So you can do this part separately. In some calculators, if you've got a calculator, it'll do it. It's quite easy to do. Or you do it on Wolfram Alpha. Or if you've got a good app on your phone, good scientific calculator that does complex numbers, you can do that one quite quick.
So now we need to invert the bottom answer.
So now we need to invert it.
So Z equals...
So that means, I'll work to the left a little bit here.
So do we need a 1 over that bottom answer? Do we need a 1 over it? Really?
Yes. Yeah. If 1 over Z equals that, that means, let's put a therefore in. Therefore, Z equals 1 over this number. 0.01646 minus J 0.0266. Okay.
Right.
So obviously to get Z I have to multiply this by its conjugate again. Do the step again. Not too bad because again you've got 1 times this with a plus on the top. Okay, so let's see if I can squeeze that in without running out of board. So Z's going to equal, I haven't got room to fit in there, Z will equal 1 over 0.01646 minus J 0.266 times its conjugate. So that's going to be on the bottom 0.01646 plus J 0.0266. My handwriting gets scruffy as I go further down. And obviously repeat that on the top to keep it balanced. So 0.266, and that equals, obviously on the top it equals that, because it's only 1 times it, and on the bottom it's going to be the conjugate. So it's going to be that squared plus that squared. So for this part of the exercise, this question, because you've already done a question where you've had to do it more manually, this one you can just do it by the cheat method, should we call it. It's not cheat method, it's a shortcut. The shortcut. So that actually gives me this 0.016. Interesting, I put the 6 there, I put the wrong number. 6, 4, oh I rounded it, 4, 6, I've rounded that to 5 in my notes, that's what I'm getting out of it. Divided by, so remember this will be a common denominator when I square that, square that. But I've split it to start with, I'm running out of boards, so I don't have a lot of choice. 9.79798 times 10 to the minus 4. So we're getting small numbers. And then it's going to be plus this time. J 0.0266, which is that part, divided by this as well, 9.798 times 10 minus 4. So we're nearly there. If I do this, divide that by that, and divide that by that, I'm going to get to, it's going to simplify it. It'll also give us a nicer set of numbers, and those are these. So Z, finally, is 16.823 plus J 27.15 ohms. So if that is my impedance of that circuit, that is Z. And that tells us something as well. It tells us that the real part, the resistance, the total resistance is 16.8, and the imaginary part, so the reactance of the circuit, is 27-ish ohms. So that's what you see when you look into that circuit. It might have all them components in, but it's only got that amount of resistance. Well, that's the total, the sum of it. The other thing as well is if I convert it to a rectangle, which you know you can do in your calculator easy, convert it to a rectangle, it'll give you the phase angle as well of the current going into the circuit, or the volts, or the power. You can work out the power triangle. All these things can be found from it. So that's where one of the, I said before about rectangle versus polar. Polar is really useful. It gives you the phase and angle.
Yeah.
And this way it's easier to add the values together sometimes in the rectangle. So both are quite convenient. Okay, so that's that finished, completed.